Hello everyone. In this video, we are going to talk about graphing rational functions. Before we begin, I made a list of things that will help us as we go through and we graph. So first of all, whenever you graph rational functions, it always helps to name the domain restrictions, figure out what x cannot be, and that's going to tell us a little bit about the graph. It's always a good idea to find the x and y-intercepts because that gives you some points that you can plot. It'll help us out. Remember, if you're finding the x-intercept, set the numerator equal to 0. And if you're finding the y-intercept, plug in 0 for x. After that, you want to find any horizontal asymptotes that the graph may have. A horizontal asymptote is a horizontal boundary for the graph. It pretty much gives you the end behavior of the graph. Many of the graphs will never ever cross a horizontal asymptote. There are a few cases where they might, but it's basically saying what number is the end of the graph getting close to. In order to find the horizontal asymptotes, what we want to do is we want to compare the degree of the numerator to the degree of the denominator. And in order to represent this, I'm using n to represent the degree of the numerator, and I'm using d to represent the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is going to be at y equals 0. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote will be y equals a ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then there's going to be no horizontal asymptotes. You'll either have a slant asymptote or a hole, and we'll talk about those cases as they arise. Then, after we find the horizontal asymptotes, we find any vertical asymptotes or holes. And honestly, you can do number 4 before you do number 3. Sometimes we do step 4 whenever we find the restrictions on the domain. So just because these are numbered doesn't mean they have to be done in this order. But what you want to do is you factor the numerator and the denominator. And then you look to see if anything cancels out. If something cancels out, set that equal to 0, and that is where the graph has a hole. You'll graph whatever's left over after that cancels out. What does not cancel out is what we call a vertical asymptote. Okay, so you use that denominator, wherever that denominator equals 0, to figure out if you either have a vertical asymptote or a hole. Okay. And then number 5, usually what I do is have pick just a couple points to the left of the vertical asymptote and a couple points to the right of the vertical asymptote just to kind of get a good shape of the graph. And then after that, we take what we know and we sketch that graph and we'll name the domain and range. So let's get started. So the first example that we have is f of x equals 3 over x minus 1. And so for this function, we're going to start out by listing any restrictions on the domain. So I'm going to take that denominator and I'm going to set it equal to 0. And we realize that x cannot be 1. So that's a restriction on the domain. That tells me something's happening at 1 on this graph and we'll have to figure out what. So the next thing I'm going to do is find any x and y intercepts. So x-intercept, basically all you need to do is set that numerator equal to 0, and you notice the numerator is just a 3, and 3 will never equal 0, so there is no x-intercept, so we're just going to say none. Okay, now we're going to find the y-intercepts. So when we find the y-intercept, we'll say y-intercept, we are just going to plug in 0 for x. So we get 3 over 0 minus 1. And 0 minus 1 is negative 1, so we get negative 3. So we have a y-intercept at negative 3. All right, after that, we're going to go through and find our asymptotes. So, horizontal asymptotes. So we're going to compare the degree of the numerator and the denominator. Now, when you do that, you are looking for your variables. So if you notice in this numerator, there's no x. So if there were an x, that would be x to the 0 power, okay? Because remember, anything to the 0 power is 1. So if there's not an x there, then that's the 0 power. In the denominator, the power is 1. So we know that 0, the degree of the numerator, is less than 1. So going back to the list that we had on the last page, we know that we have a horizontal asymptote at y equals 0, okay? Now we're going to look for any vertical asymptotes. Now, if you notice, looking at the original function here, the numerator did not factor, the denominator did not factor, nothing cancels out. So what that tells me is that there is no hole. So where that denominator equals 0, the domain restrictions, that means that we have a vertical asymptote at x equals 1. So we look at this domain restriction that we had earlier, and that lets us know that we have a vertical asymptote at x equals 1. Okay, so what I'd like to do is right now, let's go ahead and graph the asymptotes, okay? And I'm going to graph them in red. Please keep in mind that the asymptote is not part of the graph. It is just a boundary, okay? So I'm going to first graph my horizontal asymptote. I'm going to go to y equals 0, which is the x-axis. So here I have it. And then I'm going to draw my vertical asymptote at x equals 1, which goes here. There we go. Okay. I usually draw them as a dotted line just to show what they look like. I usually put arrows on both ends. So let me kind of go back and do that real quick. There we go. I'll put an arrow on this side and that side there. Okay. So those are the asymptotes. So what I know is, if y'all remember when we graphed parent functions in the last unit, that your rational functions kind of take this shape right here, okay? So when we go to graph this, we're kind of wondering, you know, is the graph going to be like this, okay? Or is it going to do like this, okay? I mean, some graphs will even do like this, just depending on the function, okay? Now, so what I want to do is just graph what we know so far. We know that there is no x-intercept, and that really makes sense because you notice how we have a horizontal asymptote along the x-axis. Well, the graph's not going to cross that, so that's why there's no x-intercept. Your y-intercept is -3, so we're going to go over and we're going to graph -3, 1, 2, 3, right here on the y-axis. Okay, so that pretty much tells me I'm pretty sure that this part of the graph is going to do something like that. Okay, and so it doesn't hurt to, like, you know, pick another point to plug in. Like if I decide, let's plug in -1 and let's figure out what the y value is at -1. So I would say like 3 over -1 minus 1, which would give me -3/2, which is -1.5. So if I go over to -1, I'm going to go down 1.5, which is going to be like right in here. Okay, so let me plot that point right there. Okay, and you can kind of see the general shape. So as long as you have a general shape, it's completely fine. It does help if we plug in like one more point. So I'm going to, right here, I'm going to plug in -2 now. And 3 over -2 minus 1, which is going to be 3 over -3, which is going to give us -1. So if I go -2, I'll go down to -1 and be like right there. So you can kind of see that shape that's taken place. And the rest of it, we're just going to kind of sketch. Kind of give it a good sketch there. Doesn't have to be completely exact. Sorry, my program doesn't like the way I'm drawing this. Okay, there we go. Doesn't have to be completely exact, but as long as you have it pretty close, okay? So now we're going to go to the right. I'm pretty sure the graph's going to be up here. I mean, knowing the nature of these graphs and all of that, I'm pretty sure that's what's going to take place. But what we're going to do is just plot a point just to make sure. So I'm going to pick a point that's to the right of that vertical asymptote that we have. So let's go with like 2. If I plug in 2, so I'll have 3 over 2 minus 1, which is going to be 3 over 1, which is 3. So at 2, we're going to graph 3. So we're going to go over 2 and up 1, over 2, up 1, 2, 3 right there. Okay, and that's honestly enough information to get a pretty good graph here. We could plug in 3 as well. If I plugged in 3 here, and I would get 3 over 2, which would be 1.5. So if I go over 3, I go up 1.5, which is about right in here. So that gives us enough to kind of give this a pretty good sketch. There we go. Okay. All right. And there you have it. So this is the graph of the rational function. Now what we need to do, we're going to list the domain and range of this function. So I'm going to say the domain. We know already that the domain skips. We've already listed it, x does not equal 1. But let's put it in interval notation. So I'm going to say the domain goes from negative infinity to 1, unioned with 1 to infinity. And then the range, it skips the horizontal asymptote, which is 0, and we're going from negative infinity to 0, unioned with 0 to infinity. And there you have it. So that is our first rational function that we're graphing. Let's do another example. So let's go down here. Okay. All right, so for this particular example, let's start with the domain. So I'm going to say that set the denominator equal to 0, x equals 0. That means x does not equal 0, so that's the restriction that we have on our domain. I'm looking at this problem, though, and I noticed something here. This numerator factors, and I can factor out an x. So I would say if it factors, you don't have to wait to do that. You can just go ahead and do that once we find that domain. So here I'm going to factor out the x, and I'm going to get x times x plus 2 over x. And then what happens, these x's will cancel out. Because they cancel out, that's where a hole is located. So I'm going to go ahead and write that down. Even though it's number 4 on my list, I'm going to go ahead and do this now. So I'm going to say we have a hole where that cancels out. So it canceled out where x equals 0, okay? So meaning that now the restriction on the domain is a hole in the graph at x equals 0. Once you cancel out, you're going to graph what is left. Okay, so let's talk about that for just a minute. Sometimes this stuff that's left will still be a fraction. Sometimes it's not. If you notice, once we canceled out that x, I'm left with just x plus 2. And that graphs a line. So if what's left is no longer a fraction, you are not going to have any asymptotes. The only thing this graph has is a hole that we have to worry about. So with that being said, I don't have to go down the list of things and find, the x-intercept, y-intercept. We don't have to find vertical asymptotes, horizontal asymptotes. All we have to do is graph that line, but just make sure that we put a hole in the spot where x equals 0. So here's what I do. I go through and I say, okay, the y-intercept of this is 2, the slope is 1. So I'm going to go to 2, and I'm going to plot that point, and I'm going to graph my slope as 1. I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, graph that slope. And I'll go down 1, left 1, down 1, left 1. So this is the line x plus 2. And then after that, I'm going to say, okay, I have a hole where x equals 0. So I'm going to come back over to my graph, and where x is 0, I'm going to erase that spot, and I'm going to go back, and I'm going to put an open circle, put a hole. And then I'm going to graph the rest of it, okay, just like this. And there I have it. And there's my graph. So let's give the domain and range for this. The domain is going from negative infinity, skips 0, and then 0 to infinity. And then the range is the y value for that whole. That's what's skipped. So we'll go negative infinity. The y value for that whole is 2, union with 2 to infinity. And there you have it. So that's another example of a rational function. It turned out to be a line with just a hole in it. Okay, so let's look at another example. All right, so here's example 3. All right, so in this case, well, let's start with the domain. So we're going to take that denominator and set it equal to 0. Now, you notice that this factors. It's the difference of two squares, so it factors into x minus 1 and x plus 1. So there's two places where this denominator equals 0. So it equals 0 at x equals 1 and x equals negative 1. So we're going to have to figure out what's going on in both of these places, okay? Sometimes the graph might have two holes. Sometimes the graph might have two vertical asymptotes. Sometimes the graph might have a hole and a vertical asymptote. So, but since we're given the domain, I'm just going to make that not equal. All right, so I'm going to go back to the original, and I'm looking at it, I'm like, well, I know that denominator factored, so I'm going to write that down. Now, the question is, did anything cancel out? And if you notice, the numerator and the denominator both have x plus 1. So that is what canceled out. So that tells me right now that there's going to be a hole where x plus 1 equals 0. And I used x plus 1 because that is what canceled out. And when I solve that, I get x equals negative 1. All right, so that means there's a hole in the graph at negative 1. Now I'm going to go back to what I have here. Once x plus 1 cancels out, what I'm left with, and let me find a place to write this, I am left with 1 over x minus 1. Because that x minus 1 is in the denominator, nothing was left in the numerator, so there's a 1. You notice that we still have a fraction, so that means there are also asymptotes, okay? Another thing that we can go ahead and do right now is, since we know there's a hole at negative 1, I'm going to take this and I'm going to plug into this part, what I have left after it canceled, just to find the y value for the hole. So I'm going to say that when I plug negative 1 in, I get 1 over negative 1 minus 1, which is negative 1/2. So that hole is going to be at negative 1, negative 1/2, okay? And that'll help me later when I go to graph, okay? So now that we've done that, let's find our asymptotes, okay? So we'll do horizontal first. It honestly doesn't matter the order that we do this in. Horizontal. So if we look at, once we have canceled out, we're now graphing what is left. We don't need to go back to this one. We don't need to go to this one. We're going to use what was left, okay? So when I'm finding the horizontal, vertical asymptotes, I'm going to go with this, okay? So when I look, I notice that in the numerator, there's no x, so that means the degree of the numerator is 0. In the denominator, x is to the first power, so that degree is 1. 0 is less than 1, so we have a horizontal asymptote at y equals 0. Okay, so now let's find vertical asymptotes. So vertical asymptote, we notice the denominator, we have x minus 1, and that's what's in the denominator. Nothing else cancels out, so that's going to give me my vertical asymptote. X minus 1 equals 0, x equals 1. So there's the vertical asymptote. So this is an example of a graph that will have both a hole, and vertical asymptote and horizontal asymptote. So now let's graph. I'm going to start with the asymptote. So I'm going to graph the horizontal asymptote at y equals 0. Okay. And put my arrow on that end. And then now we're going to graph x equals 1, vertical asymptote. I promise you these are not going to always be the asymptotes. Just the first two examples had the same ones. All right, and now we can graph our function. And I think I might change the color so you can see it better on the graph. Okay, so now we know that we have a whole at -1, -1/2. And you know, I'm going to go ahead and put that there. So we're going to do -1 and -1/2. I'll put a hole right there. And one thing I did not do is I did not find the x and y intercepts. So let's go back and do that. Again, when we find the x and y intercepts, we're going to go with what we have after we cancel out. So x-intercept, where the numerator equals 0, but there is no place where that numerator equals 0, so there is none. So we'd say none. Y-intercept, plug in 0 for x, so we get 1 over -1, which is going to be -1. So y-intercept is at -1, so we're going to graph that right here. Okay, so you can kind of tell, you know, like both of these points are down here, so you can kind of tell the graph's going to do that. Okay, so we can go ahead and graph that part. We're pretty sure what it looks like. We're just going to sketch. We're just skipping where that hole is, and it looks something like that. Okay, and now we'll go to the right of that vertical asymptote. I'm pretty sure it's going to be right up in here. I'm just going to pick a point to plot just to make sure. So I'm going to plug in 2. Again, I'm going to plug it into what was left over here. So I'm going to plug in 2. I get 1 over 2 minus 1, which is going to give me 1. So I'm going to go to 2 and up 1, and that point's going to be right there. So now it's safe to just go ahead and graph what we have. And there you have it. Okay, now let's give the domain and range. So domain, it goes from -infinity. Now you notice that with the domain, there were 2 restrictions, okay? So this one was where we had the hole right here. So it skips that. And then this is where we had the vertical asymptote here, and it skips that. So there's 2 places that the domain skips, which would be -1, unioned with -1 to 1, and then unioned with 1 to infinity. We have to make sure we include all of those domain restrictions. And now for the range, from -infinity, so the range comes from -infinity, it comes up, it skips this y value, okay, so that would be -infinity, that y value is -1/2, unioned with -1/2, and then once it hits this and skips that, then it goes up, gets close to the x-axis without touching it, so that would be a y value of 0, and then unioned with 0 to infinity. And there you have it, and that is the range. Okay? All right, let's do another example. We're going to go to number 4 now. All right, with number 4, so let's start with the domain restrictions. Set that denominator equal to 0. Okay, so x will not be -1/3. So we have to decide, is it going to be a whole or a vertical asymptote? And I'm sure you guys can look at that and tell already. If I factor that numerator, the only thing that factors is a 2. And I get 2 times x minus 2. Denominator does not factor. You notice nothing cancels out. So it's safe to say that's going to be a vertical asymptote. Okay, so no whole for this one. So now let's find our x and y intercepts before I forget to do that again. All right, x-intercept, we'll set that numerator equal to 0. 2x minus 4 equals 0, so x equals 2. That means, sorry, didn't mean to write that. X equals 2 is our x-intercept. And then our y-intercept, we're going to plug in 0 for x. And when we do that, we get -4 over 1, which is going to be -4. So we have our x and y intercepts. So now let's find horizontal asymptotes. Okay, horizontal asymptote. We're going to compare the degree of the numerator to the denominator. But I'm going to erase this because we don't really need that anymore. So the degree of the numerator is 1. The degree of the denominator is 1. And so we're going that they equal each other, so now we're going to have a ratio of leading coefficients. So 1 equals 1, ratio of leading coefficients, y equals. So what that means is that we're going to find out, this is the x with the highest power, this is the x with the highest power. We're going to look at the coefficients in front of them. So that would be 2 over 3. So that is where my horizontal asymptote is going to be, at 2 over 3. Okay. Now, vertical asymptotes, we already know because there are no holes. The vertical asymptote is going to be at this domain restriction right here. So we have x equals negative 1/3. Okay. So we're going to come over to our graph. I'm going to go ahead and graph those, and then we'll go back and plot points and things like that. So horizontal asymptote this time is now at 2/3. So we'll just kind of estimate that. 2/3 is kind of not quite 1, but pretty close to it. It's going to be along here. Okay. And then our vertical asymptote is at negative 1/3. So I'm going to go down to the left to negative 1/3, which is going to be like kind of like in here. All right, let me see if I can extend that out. Can't quite get it straight there. All right, there we go. Pretty close. So that's my vertical asymptote. There's my horizontal asymptote. Now let's plot the points that we know. We know x-intercept's at 2, so we're going to go over to 2 on the x-axis and plot it right there. We know we have a y-intercept at negative 4, so I'm going to go 1, 2, 3, 4 right here. So we're pretty certain that over here on the right side of that asymptote, it does this. So it doesn't have to be exact as long as you have the right shape for it, looking like this. Okay, there we go. All right. So I'm pretty sure that the other half of this graph is going to be up in here, okay? So let's plot a couple points just to double check. So I'm going to plug in like negative 1. So I'll say 2 times negative 1 minus 4 over 3 times negative 1 plus 1. So what's that? Negative 2 minus 4, negative 6. Negative 3 plus 1 is negative 2, so I get 3. So yes, it's going to be up. We're going to go up, so we plugged in negative 1, and we're going to go up to 3. 1, 2, 3, which is right here. And so I'm pretty safe to say that this part of the graph is going to do this. You could plot more points if you want to, but that's enough to give us a good graph. Okay? So now let's give that domain and range. So domain, we're going from negative infinity to the vertical asymptote at negative 1/3, unioned with negative 1/3 to infinity. And then the range, negative infinity to 2/3, unioned with 2/3 to infinity. Make that look a little bit better. And there you have it. Okay? All right, let's look at another example. There are so many different types of these graphs, okay? All right, so number 5, this one's an interesting graph, okay? So let's set that denominator equal to 0. And you notice that this does factor. So we get what? X plus 2 and x minus 1. So x does not equal negative 2 and x does not equal 1. So there's two things going on. 2 holes, 2 vertical asymptotes, one of each. Well, let's find out. All right, so when I go back to the original, you'll notice that this numerator does not factor. So nothing cancels out. So we do not have a hole, so guess what? That means we have 2 vertical asymptotes, so sometimes that will happen, okay? So let's find our x and y intercepts. X-intercept is where the numerator equals 0. So x equals 0 is the x-intercept. Y-intercept, plug in 0 for x, and I end up with 0 over negative 2, which is just going to be 0. So it looks like 0, 0 is our x and y-intercept. That's the point that we have. Horizontal asymptote. Okay, this is a case we haven't had yet. So what we're going to do is we're going to compare the degree of the numerator to the highest degree of the denominator. So the degree of the numerator would be x to the first power. The highest degree here is x squared. So we are comparing 1 to 2. 1 is less than 2. So we have a horizontal asymptote at y equals 0. Okay. Vertical asymptote, we already said there are 2 of them, okay? So we're going to find out in just a little bit what happens when we have 2 vertical asymptotes, okay? So x equals -2 and x equals 1. All right, so let's go over here and let's graph those asymptotes. So horizontal on the x-axis, okay? Let me fix my arrow over here. And then vertical, we have x equals -2, so we're going to go to -2 and draw that one. Okay, there we go. And then for our next vertical, it's going to be at 1, so we're going to draw that one. Okay, and there we have it. Okay, let's plot the points that we know. All right, so we're going to plot that one xy intercept that we have is at 0, 0. Do y'all notice what happened here? So the horizontal asymptote is a boundary, okay? But like I said earlier, it determines like end behavior. So sometimes in the center of the graph, that function might cross the horizontal asymptote. It just will not cross it like at the ends of the graph, okay? Especially when there's 2 vertical asymptotes, there's a huge possibility that the graph's going to cross right there in the middle, okay? So now we got to do a little bit of work. We've got to figure out where this graph's located. Like, am I going to have a piece here, or I'm going to have a piece here? Is it going to be here? Is it going to be here? What on earth is going on in the middle? Okay, so let's see what's going on. So I'm going to start with the left side. Since my first vertical asymptote is at -2, I'm going to pick a number smaller than -2 and I'm going to plug in. So let's do like -3. So if I plug in -3, I get 3 times -3 over -3 squared plus -3 minus 2. Let's see what that gives us. What, -9 over 9 minus 5, which is 4. So -9/4. Now you notice this is going to be negative, right? And 4 goes into 9 twice, so -2 and 1/4. So we're going to go to -3, 1, 2, 3, down 2, just a little bit past that, so somewhere right in here. Okay, 2 and 1/4, -2 and 1/4. So that's enough information because we know where the graph's located to just give a sketch. You could plug in more points, but I'm okay with you just kind of sketching that to show that it's in this part of the graph. Okay, there we have it. All right, now I'm going to go to the right of the rightmost asymptote, and then we'll come back to that middle because that middle does some crazy things sometimes. So I'm going to plug in this time. Let's plug in a number that's to the right. I'll just erase all that. All right, I'm plugging a number to the right of this vertical asymptote. So since that's 1, let's plug in 2. Okay, 2 squared plus 2 minus 2. These cancel out. So I have 6 over 4, which is 3/2, which is 1 1/2. So if I go to 2, I'm going to go up 1 1/2, which is like right there. So that's enough information to tell me that my graph's going to do this. Okay. Okay. Now, the stuff in the middle. Haha, that's where it gets really crazy. You notice there's not a whole lot of space in the middle to work with to plug numbers in. So for instance, I mean, if I'm plugging in an integer, really all I got is -1. So we'll start there. Let's plug in -1. Okay, plug in -1, -1 squared plus -1 minus 2. I get -3 over 1 minus 3, which is -2, so I get 3/2. Okay, so at -1, we're at 3/2, which is right there. Now here's where the craziness happens, okay? The stuff in the middle. Stuff in the middle can do something like that, or the stuff in the middle can do something like that. Okay, so I kind of need to know, like, over here what's happening. So we're going to plug in a half. So let's see what happens when we plug in a half. Okay. All right, plug in a half. So 1/2. So it's 3/2 over 1/4 plus a half minus 2. So 3/2 over 3/4 minus 2. Common denominator, so that'll be 3 minus 8. So -5/4 and 3/2. Now already we know this is going to be a negative. So we know because a positive divided by a negative, so it's going to be down here. Okay, so we already know that. So we have 3/2 times -4/5. So we have what? -6/5, so a little bit more than -1. A little bit, I should say less than -1. So if I go to half, I'm going to go like right below -1. That's probably going to be right here. Now you can pick more numbers to plug in. I mean, you could plug in 2/3, 3/4. You could plug in -1.5 to figure out, the shape of this. But this is enough information to kind of give us an idea that the center of this graph is going to do something like this. Okay, so there you have it. Okay, now I'm going to erase all this stuff and we're going to do domain and range. Okay. Now range we can do pretty easy now because that center piece, you notice that it went past that asymptote, and so the range is going to be all real numbers, -infinity to +infinity, but that domain skips both of those vertical asymptotes, so we'll have -infinity to -2, unioned with -2 to 1, unioned with 1 to infinity. And then the range, all real numbers, -infinity, +infinity. There you have it. Okay, we're going to do one more example, and then in this video, I did not do any examples of slant asymptotes. We will hit that in a different video. Okay. All right, so let's look at this one. F of x equals x cubed divided by x. The restrictions on that domain, x cannot be 0. Okay. And you notice that we have x cubed and we have x to the first power, and we can simplify that down. We can cancel out an x. So this x will go into that, leave 2, so we're left with x squared. Now since we canceled out an x, that means there is a hole where x equals 0. So this domain restriction means that we have a hole where x equals 0. And if you remember, like a previous example that we did, you always graph what's left and look at what we have left. This is a parabola, okay? So parabolas do not have asymptotes. There's no fraction left. So we're going to graph x squared, but we have to put a hole where x equals 0. So if I plug 0 into x squared, I get 0, so the hole is going to be at 0, 0. And we've done a lot of graphing of parabolas, so I'm just going to go ahead and put that open circle here, 0, 0. And the pattern for our parabola goes to the right 1, up 1, to the right 2, up 4, 1, 2, 3, 4, to the right 3, up 9. And then the left side does the same thing. Left 1, up 1, left 2, up 4, left 3, up 9. And it looks like this. Okay, there you have it. Okay, the domain, -infinity skips 0, union with 0 to infinity, and that range, you notice there's a hole at the lowest point right here. The lowest point for y has a hole, so that means it does not equal 0, but it does start there. So it'll be parentheses 0 to infinity. And there you have it. That's our lesson on graphing rational functions. We will get to slants in another video. Thank you, hopes. We're going to compare the degree of the numerator to, sorry, I hit